But because of that, we were here. I suppose we were discussing about the rescue robotics in our last lecture, and we were discussing that there are these instances where robots have been used in rescue, and this was at the World Trade Center, where we had robots from the University of South Florida, and they were used in rescue robotics. It's a very noble cause, very useful one. You must have also heard of the incident of Fukushima in Japan. How many of you have heard about the incident of Fukushima?
Yes, sir. Fukushima nuclear disaster.
Yeah, so you must be aware that there was a very huge tidal wave, and that was caused due to an earthquake of almost of more than 9 on the Richter scale in Japan, and then a huge tidal wave was generated, and that tidal wave it almost swept the power plants at Fukushima, and they were. I mean, there was a lot of trouble over there. Now, a lot of damage was caused. Uh, those could have been used at that time, but a lot of lives were also lost because rescue robotics couldn't be put to such good use at that point of time. You must be aware that Japan is very advanced in robotics. They had invested a lot on humanoid robotics, and in fact, several years back, they had also completed the second humanoid robotics project. That was part two. But at the time of Fukushima, um, they were unprepared for it because possibly they had never expected it, or they had never focused on rescue robotics to such an extent. And so perhaps the Japanese must have focused more on personal robotics, on uh, other fancy forms of robotics, which may have been more appealing to people, maybe in manufacturing as well. But as far as rescue robotics was concerned, this is one place where one of the most advanced nations in the area of robotics, it uh, it was helpless at that point of time. So it's very important that we work in the right direction, and we should have our objectives clear. So robotics is certainly extremely useful in the rescue robotics area as well. You have mobile robots. These are very old videos. So you have uh, mobile videos. You can see them handling a ball in a game. Here is another version of a tree climbing robo, not the one which you saw in the video yesterday, but this is a one before that. It's much older, used for climbing of trees, palm trees, and it's based on a pipe climbing robotic mechanism. It's where parallel manipulators configurations. Um, We have also wall climbing robots, different models which have been prepared over several years in the past. There are other applications of robotics, especially in prosthesis, in development of prosthesis. You must be aware that uh, you can provide artificial limbs to human beings, and if you can make the limbs functional just as the natural limbs do, you succeed in developing a good prosthesis. And there are several challenges associated with this. See, in human tasks are easy to perform. We take our limbs for granted almost. Um, Say, if we want to hold an object, we can hold it very easily. We don't even think about holding an object. Uh, we can when we can manipulate it. When we say manipulate, we mean we can translate or rotate it. Okay, we can translate it or we can rotate it. Uh, we can estimate and distinguish its inertial properties. Can estimate and distinguish its inertial properties means what? We can uh, connect with its mass and the rotary inertia. We can't say exactly what this mass is or how much this rotary inertia is, but we can certainly compare with other. So in case of a standard, if we have a standard and we hold it and we move it, we can compare it with another uh, mass whose mass is not known and inertia is rotary inertia is not known. So we can, so this sense, this ability of human beings is taken for granted. But all this is quite difficult for robotic systems. Uh, you have several challenges in human systems. You have enormous redundancy, means you have more number of limbs and joints, actuators than that are needed to control those degrees of freedom which are provided to us. We have excessive number of degrees of freedom. So you also have sensors, actuators, and controls. Uh, there are too many, and they're all networked with the central nervous system. Um, the central nervous system, a lot of research goes on in this. It's still complex and it's not very well understood. I mean, there is progress on understanding it. We try to understand it, how things are learned, how things are improved, how things are controlled, what is the response. Many such kind of aspects are studied. In prosthesis, we deal with rigid skeletal links, with soft materials and sensors and actuators embedded on these, and integration with intelligent systems. There are several challenges. We deal with non-rigid devices, soft materials with distributed sensing, where you can use layers of polymeric film, uh, piezoelectric material, semiconductor resistive, and piezo resistive material. A lot of ways of fabrication of these films by deposition, etching, fabric weaving, lines of sensory material. A lot of techniques are available. A large number of signal lines, uh, they emanate from the soft material. Now, this is if you want to instrument the prosthesis with sensory abilities. You have to do data acquisition in the presence of noise and lots of data acquisition distributed over an area. Control of redundant flexible actuation system. This is another challenge. Integration with electromyographic signals. You have to obtain signals from your muscles externally, not by putting electrodes inside, but just outside on the surface. And the signals that you get, uh, you have to integrate it with your control system, and you have to determine actually uh, what is the meaning of these electromyographic signals. Distributed regions to discrete state controllers. You see, you have uh, control to be performed over an area, over a distributed area, and this has to be done through discrete state controllers. So you're mapping from a continuum to a discrete system. So it's a challenging exercise. There are very interesting mechanisms which we have developed in our work on robotics. We'll discuss with you all some other time, but this is just to give you a glimpse in development of prosthetic systems where we have the unlike configuration and the like configuration, and how prosthesis or prosthetic devices are used. So just to give you an idea, suppose you have a situation where person has lost a thumb, let us say, and you want to replace that part. Okay? You want to place a thumb, an artificial thumb, with movement abilities, so that it can behave somewhat like a natural thumb. So in order to do that, you can pass on motion from a good finger to this prosthetic, passive prosthetic finger. So let us say that the good finger is over here and the passive prosthetic finger is here. Okay, this is what is your artificial finger. And you want to pass on motion from here to here. So in this case, how do you do it? What you can do is you can connect linkages like this, one to the good part, that is the active part. In this case, let us just analyze one joint here. Okay, here you have a joint, and here you have a string which is wound like this. Okay, now this string, there are two strings. There is one in blue and there is one in red. Now these strings are not just strings by themselves; they are actually passing through a tube. So it's a string tube combination. It's called a Bowden cable combination also, but we'll call it a string tube combination. In the string tube combination, the tube terminates on the distal link, on the proximal link, not the distal, on the proximal link. Okay, so it terminates here, and the string which passes through it, it terminates on the distal link. Okay, so when you pull the string, there is relative motion of the string with respect to the tube, and you can see this pulley which is at the base of this link, that will result in its motion, and the point A2 will open up. It will open up like this in the counterclockwise direction when you pull this blue string. Okay. In the same way, for the red string, the sense of winding is different. So you have winding in the opposite sense. Again, here you have the tube terminating on the proximal link and the string terminating on the distal link. So when you pull this red string through this tube, this is going to pull and it is going to give a closing motion. So by pulling these two strings, the blue and the red one, at different times, you can obtain motion in the counterclockwise or the clockwise directions respectively. Now when you do that, when you do this, you can also wind, now this is all part of the tube. So the string tube, it's a string tube combination. The same tube also terminates here. The other end of the tube terminates here on the proximal link of the passive joint, of the prosthetic joint. And through it, the string passes. But now you can see the sense is opposite. It was like this, it passes like this, and then it goes like this. Same thing for the red one. Here also it goes like this, and sense of string is here. The tube terminates here and the string terminates here. So when you pull the red one, naturally it's going to open up. Now this particular configuration is called an unlike configuration because when you move the active joint clockwise, the passive joint moves counterclockwise. When you move the active joint counterclockwise, the passive joint moves clockwise. So it's called an unlike configuration. Now you may note over here that you are actually transferring motion from a good finger to a passive prosthetic finger. And it does not matter, it is not necessary that the axis of these two fingers should be parallel or they should be at fixed distances. They may move. Actually, our fingers, they continuously move. And that's why when you make use of this Bowden cable, so you have flexibility available. So this is a design which we had patented while in Japan. Um, the same design can also be used for like configuration. Suppose you want to augment the motion of your joints, the other fingers, with uh, motion from the good fingers. So you can move, say, for example, you can pass on motion from the index finger and the middle finger to the ring finger and the little finger. Okay, because you see that their motion is in the like configuration. So when the index finger moves like this, the other fingers also move in the same direction. They are not opposite, but the thumb moves in the opposite direction. So as far as the thumb is concerned, it is in unlike configuration with the others. And as far as these fingers are concerned, they are in like configuration. So these are simple principles which we have developed. You can switch on from the unlike configuration to the like configuration through a very simple trick. All that you have to do is turn this axis, turn about this axis by 180 degrees. Okay. Automatically the sense of winding will appear to be reversed, and you will switch over from the unlike configuration to the like configuration. So this is a very simple mechanism for transferring motion, passive motion through active joints. Uh, we won't dwell much on this. We have also modeled these using, because we have to model and simulate these. So in our laboratory also we do a lot of work on modeling of prosthetic systems. And there are other alternatives for the like unlike configuration also, which were developed, which have been published. And I think it may be worthwhile if you can see them, different alternatives. I'll just give you um, an idea if it works, if the video works, it will be good. I think the link is not available. I'll have to set the link. Yeah, so it's a video, but it's not activated. The link is not connected properly, I think. Okay, here also, let's see. Oh no. So maybe some other time I'll show it to you. But let us explore the other aspects of robotics. Okay, for teaching, for learning, you have a number of objectives: designing, controlling, programming, robotics, and embedded systems. You have the challenges associated uh, with establishing the curricula, teaching platforms, labs and projects with solutions, and integrating together different mechanical engineering, electrical engineering, computer science, control systems, etc. So, a mechatronics job in that sense. And there are several opportunities of teaching embedded systems, computation for interacting with physical systems, making intelligent autonomous machines, and hobbies. So teaching robotics also can be very interesting. I'm not going into these things. There are a number of things which are there. There are several resources available, and I'll be sharing this video link with you all. Also the previous lectures video. So please don't have to worry about this. You will get it. There are several books and journals. The basic texts you have already seen, we have discussed yesterday. Of course, we will be following the book by John J. Craig. There's the second one over here. It is extremely popular, especially for undergraduate and graduate references. So this is a very good book. Okay, this is what we'll be following. This is mathematical, but it's if you want to pursue a research career in robotics, this is a good book. Okay. You have a very good exposure provided in the other books as well. There is a book by Professor Saha, which I also discussed yesterday. For control systems, we have resources. We have the book by Katsuhiko Ogata on system dynamics. He also has a book on modern control engineering. We have the book by Benjamin C. Kuo, which is very popular. There is a book by Carnot, Margolis, and Rosenberg, which makes use of bond graph system dynamics, modeling, and simulation of mechatronic systems. There's a book by Ranjit Karmakar and Professor Amlendu Mukherjee from IIT Kharagpur on modeling and simulation of engineering systems through bond graphs. There are several resources that are available for this. There are several reference topics, and there are several journals in which you can obtain, in which you can observe articles on robotics. And most popular among these are the International Journal of Robotics Research. You have IEEE transactions on robotics, ASME IEEE transactions on mechatronics. You have Mechanism and Machine Theory, which is an Elsevier publication, which also carries several articles. You have an ASME journal on robotics and mechanisms. You have another journal by ASME that is on dynamic systems measurement and control. So very popular journal, and a lot of articles on bond graph, system dynamics and control, and robotics. They are published in this journal. So there are. So let us just proceed now. There are several other applications which we will discuss as we proceed with our lectures. Okay. So as far as this is concerned, I am just going to now proceed towards the kinematics of robotics. Now, in kinematics, you must be knowing that it deals mainly with the geometry and geometry of motion. So we will be dealing with positions, with velocities, accelerations, orientations, angular velocities, angular accelerations, quantities like this. That is because we are not interested, while dealing with kinematics, we are not interested, or rather we are not exploring the causes of the motion. We are just studying the motion. So what is it that causes this kinematics? This is not what we explore in kinematics, but we just analyze whether with this kind of linkages, whether this kind of configurations, we are able to obtain the desired kind of motion. So that is kinematics. Now in kinematics, now we are going to start from first principles, absolutely a raw. So please, those of you who have any prior notions in your mind that things are difficult, please keep them aside. We are going to now go from the start. Okay. Now, if you see, let's start with notation for vectors, the one which we are going to adopt, because ultimately we are going to use a matrix way of representation. And this matrix way of representation helps us in using the digital computer in doing computational manipulation, okay, computational tasks using matrices. It's very convenient, and one can use MATLAB or Scilab for such purposes. Now, for this notation for vectors, so we have a point P and we have a point Q. Let's say we have these 2 points, and we have a vector from Q to P. So we will write this vector as the position of point P with respect to Q. We'll write it as R with a bar on it, and this is what it will mean, that is going from Q to P. So it's position of P with respect to Q. Now, if we want to specify the location of this point P, then we have to have a reference frame. What we have shown here is the reference frame 0. Okay. Usually for reference frames, we put them in curly brackets. But I think this being one of my earlier slides, this still remains to be done. Just skip my attention. So we can specify this vector with respect when we express it in this particular frame 0. So let's say that we have along the x direction, we have the component, that is the distance measured from the origin over here, that is x of P with respect to Q. And this distance is measured in the frame 0. So you have to walk along the x axis and measure this distance. So if you use a measuring tape, you'll get this distance. You know its direction as well. So this is the x component. Similarly, we have the y component of this and the z component. Now, how did we obtain these components of P? We just resolved them. So we dropped a perpendicular from the point P to the plane xy, and wherever it intersected here on this plane, then we again resolved, we drew a line parallel to the y-axis, draw a line parallel to the x-axis, and then we obtained these components. So this length from here to here was x, this was y, and this length here is z. So these are our component vectors. When we add these vectorially, we obtain this vector q to p. So we can write the components of this vector. The components of these vector are xp, this one, yp with respect to q expressed in 0, and zp with respect to q expressed in 0. So these are scalar values. Okay, depending upon their sign, we just know the direction of the measurement. So the x component, y component, and z component of this vector p with respect to q and expressed in the frame 0. See, this is frame 0. So this vector, it's a matrix representation of this position vector. So it's the position of point P with respect to Q and expressed in the frame 0. Now let us take another frame. Let us take the frame 1. Now this frame 1, if we take the same vector but now resolve this same vector qp, that is p with respect to q, but we resolve it along the directions of the frame 1, we will get x component, y component, and z. In order to resolve it, we follow the same technique. We draw a perpendicular from here, we drop it on the xy plane, on this plane which is formed by these two vectors, and then wherever it meets, we then draw a line parallel to this axis and draw a line parallel to this axis, and then we have the three components available: xp, yp, and zp. Okay. So if we are to represent the same vector in this red frame, frame 1, we'll express it like this in terms of three different components: xp with respect to q in the frame 1, yp with respect to q in the frame 1, zp with respect to q in the. Okay. Now, how do we distinguish? You see, what is the difference between these two? This vector is expressed in the frame 0, and this vector is expressed in the frame 1. The vector is the same. Geometrically, it appears to be the same. But the components, when measured in different reference frames, they are different. Okay. Now, we can relate these two vectors, these two representations rather. The vector is the same, but we can relate them. How? So, this vector and this vector can be related through a transformation. And this transformation, you see, this is a 3 by 1 vector, this is a 3 by 1. So this transformation, when you just transform, when you just operate it on this vector, you should get this vector, which is a 3 by 1. So what should be the order of this matrix? Can anyone tell me? Yes? Are you all paying attention?
So 3, 3.
2 by 3.
1 into 3.
1 by 3.
3 by 3.
1 by 1.
See, this is a 3 by 1. This is a 3 by 1. So what should be the order of this R?
3 by 3.
3 by
It should
3.
be 3 by 3. You are right. You are right. So if we just write it, this is 3 by, sorry. So this is 3 by 1. This is also 3 by 1. So this has to be 3 by 3. Okay. Now, I think I will proceed step by step instead of directly putting this before you. So we have got this slide here, and we will just make our explanations on this slide. Now you see, we can write this vector, position of the point P with respect to Q in the frame 0. We can write it, I think let me take a new page, it might be better. Yeah. So we can take this vector, the position of the point P with respect to Q, expressed in the frame 0. And we have three components for these. What are these? We have position of the point P with respect to Q in the frame 0. When we write it using our unit vectors, I, J, K, we make use of the unit vector in the frame 0. I in the frame 0, okay, plus yp with respect to q. These are just scalars, okay, this yp, xp, yp and zp. But here we have this unit vector j plus we have z p with respect to q in the frame C. This is in k. This is multiplied by the unit vector k, k0. So I0, J0, K0 are the unit vectors of the frame 0. And we also have the representation, same thing. We can write it as same vector. We can write it as x p with respect to, sorry, xp in the frame 1, making use of the unit vector of the frame 1. Okay, so the component here, this is the red component, okay, plus y t with respect to q, unit vector j in the frame 1, plus z p with respect to q in the frame k. Okay, the vector is the same. Now the point is, if I am interested in obtaining xp, x with respect to q in the frame 0, how can I obtain it? What should I do to this equation just to have xp with respect to q in the frame 0 on the left hand side? All the other terms on the left hand side should vanish, and we should have other whatever terms needed on the right hand side. What operation should we do? Can you tell me? Anybody? Suppose we take a dot product.
Dot and
Yeah, if we take a dot product of, if we just multiply, that is, if we take the dot product with I naught vector, then what happens? So here we can have I naught dot I naught. Okay, we can have this here. Then here we will have y t with respect to q. Here we will have j naught dot I naught, because we are taking dot product. Okay, plus zp q0 k naught dot I naught. So on the left hand side, we have multiplied, or we have taken the dot product with I naught. Here also we are going to take the dot product with the same I naught. So here we will have xp. In fact, okay, let us write this as x. So this is I1 dot I naught plus y is equal to 1 j, this will be j1 dot I naught And lastly, here we will have plus Z E with respect to Q frame 1. And this is K 1 dot I. Okay, so what we have done is just taken the dot product with I naught on both sides. Now what will happen here? Uh, what is I naught dot I naught?
1,
1.
1,
1. So this is going to be just XP with respect to Q in the frame. Just a moment, please hold. Excuse me. So here we have XP. So this will be 1. What will this be? J naught dot I naught?
0,
0.
0. What about K naught dot I naught? 0. So we are left with XP over here. And what do we have on the right hand side? What do we have on the right hand side here? You see,
XPU1.
1.
we can write, let us keep here XP with respect to Q in the frame 1. We'll keep here YP with respect to Q in the frame 1 and ZP with respect to Q in the frame 1. And I'm going to use a let's say place it in box like this. Okay, it's a vector, so I'm just going to use this. So this is a 3 by 1 vector. Okay. Now we will have to use another box here, 1 by 3 box. Okay, and write down the components here in it. What are those components? So we'll have here I1 dot I naught. Okay, this multiplied by this. Okay. And here in the middle we will have J1 dot I naught. Okay. And here we will have K1 dot I. Okay. So here we have a matrix like this. It's a 1 by 3. When this is multiplied by this, we get this right hand side. Okay. So in the same way, we can continue this exercise. We can write down the second row, that is YP, when we just want YP with respect to Q in the frame 0. What are we going to get? Here, we'll have the next box here. So we'll have this box here. And the same way, we'll also have one more box here. So in order to obtain YP, what should we have? We should eliminate this part and this part, right? So we'll take dot product with J naught on both sides.
Yes, sir.
So when we do that, what are we going to get? I naught dot J naught will be 0. J naught dot J naught will be 1. So we'll be left with YP with respect to Q expressed in the frame 0. This part also will go to 0. And here we will be left with I1 dot J naught Okay. Then here we will have J1 dot J0, and here we will have K1 dot J0. Okay, so you will have this multiplied by this, plus this multiplied by this, plus this multiplied by this. Okay, and in the same way, Z T with respect to Q in the frame 0 will be written as I1 with respect. This is K naught. This will be J1 K naught, and here it will be K1 dot K. Okay. So what we have got here is a matrix here. You see, we have now been able to relate. We are now able to relate this vector here with the vector here. This vector was what? You see, this vector was position of the point P with respect to Q expressed in the frame 0, and it was a 3/1 vector. Okay, 3/1 vector. Here we have got the position of the point P with respect to Q, but now it is expressed in terms of the frame 1. Okay, but now relating these two, we have got a transformation matrix in here in between, which is a 3/3 matrix. Okay, this matrix here is what we call as R1 to 0, because you are transforming from 1 to 0. So this matrix that we have here is called as an R matrix. It's an orientation matrix or an R matrix. Okay, it's a very special matrix. We will discuss about its properties in our class tomorrow. So I think we have exceeded our time. Let's stop here for today. Anyone having any queries?